So it's lecture 12. And I had said it in the last lecture that the graded exams will be returned today. They will. I'll post the results right after the lecture. Okay, so last time we kind of like entered this whole new world of so-called abstract linear algebra, where we talked about vector spaces. So this included some new types of vectors that we hadn't seen before. For example, polynomials. Then we had a vector space of functions. We talked about subspaces, which is pretty much the same definition. Then we revisited all our previous definitions of linear combination, span, linear independence, and they're exactly the same. They just use whatever the new notion of addition and scalar multiplication is in the vector space. And then we introduced the notion of a linear transformation. And this again is just a function that preserves linear combinations. And one important example of this that we saw is differentiation, going from the vector space of differentiable functions to the space of all functions. Now, what we're going to do in this lecture is we're going to continue to develop the theory of linear algebra in this more general setting. So I want to show you three things. So one is I want to talk about, we talked about linear transformations. I want to talk about invertible linear transformations, which are very important in linear algebra and have a special name. They're called isomorphisms. So these are just invertible linear transformations. Then I want to talk more about the concept of a basis. So we introduced a basis of Rn, or a basis of a subspace, before the midterm. Now we'll talk about a basis of a general vector space, and we'll introduce another very useful thing you can do with a basis, which is assign coordinates to vectors. And then finally, we will use these concepts of isomorphisms and basis and coordinates to to prove, I guess, actually a very simple fact, which I'm going to call the correspondence principle. Which is a particular type of isomorphism ultimately, but really what it is it's a way to reduce linear algebra in some general vector space V back to linear algebra in Rn. So from the perspective of solving problems, it's very useful. Okay, so we're going to see that even in this big new generality, there's somehow a way to reduce everything back to Rn anyway, at least in a lot of cases. Okay, so let me begin with item 1. So I'm going to define, so an isomorphism is an invertible linear transformation. And remember, invertible means one-to-one and onto. So let me remind us, let me just say what one-to-one and onto mean in terms of linear transformations and some subspaces associated with them. So here's a definition. So given a linear transformation, T going from some vector space V to some vector space W, the kernel of T, denoted ker of T, is the set of vectors in the domain, so that T of x equals 0. So this might look familiar because this is very much like the null space of a matrix, except now it's a linear transformation. So this is a subset of which vector space? Is it V or W? Okay, V, yeah. It says these vectors are in V, okay? So, and then the range of T, again, almost the same definition, just for linear transformation set of matrices, it's a set of all vectors in the codomain, so that T of X equals B has at least one solution. So it's not really a new concept. It's the same concept in a slightly more general setting. Okay, so this is called the image of T. And these are both subspaces, okay? You can just check that from the definition. Remember, to be a subspace, you have to be closed under a scalar multiplication and addition. So these are, generalization of null space and column space of a matrix. So I'll just add that here. So this is this is kind of like null space of a matrix, and this is kind of like column space of a matrix. But really, it's something taking place in this more general setting. And now, given these things, I can define one-to-one and onto in terms of these subspaces, just like I did before. So T is onto if the range of T is actually equal to the codomain, which just says that for every B in the codomain, Tx equals B has at least one solution. And it's one-to-one. It's literally the same definition, except with these slightly new words. If the kernel of T equals just the trivial subspace, which turns out to be the same as saying that for every B in the codomain, Tx of B has at most one solution. And this IE is not, it's not literally obvious, right? On the left-hand side, I'm looking at solutions of Tx equals 0. On the right-hand side, I'm asking about Tx equals B. So there's a little proof that goes here, and it's very similar to the relationship between solutions to homogeneous and inhomogeneous systems. So I won't do it. You can do it on the homework. But these are the definitions. So any questions about these definitions? I'm going to show examples in a moment, but any questions about what's written in the definitions?
So this is more general than just saying for a specific vector, right?
What do you mean a specific vector?
So before we said one-to-one and onto for specific matrices, which were the columns of vector of multiple vector, and this is more general than just a vector.
That's right. So a special case of this. So maybe I should be more precise. A special case of this is that this is equal to the null space of a maybe you're by vectors you really mean a matrix, I guess.
Yeah.
So this is equal to the null space of A. Whoa. By the way, this is a linear transformation. But anyway, this is equal to the null space of A for TA for the linear transformation, which just multiplies a vector by X. So that's the connection to the previous concept. But yeah, as I'll show you in a moment, there are linear transformations that are not don't come from matrices. So equals call A for dA of X equals AX. So I guess for T of X, because I'm just calling it T, right? Yeah. Any other question about the definitions? Somebody's asking a great question. Is there a Goldilocks theorem connecting one-to-one and onto for our new definitions? Great question. I'm going to come to that later in the lecture. But before that, let's look at some examples. So we look at some new examples that didn't exist in Rn. So for example, I have the linear transformation from this set of differentiable functions to a set of all functions that takes a function and differentiates it. Sorry. So what do I, for example, if I apply this to the function sine x, which is a vector in D, what vector do I get?
Cosine x.
Cosine x, yeah. So this is a linear transformation as we discussed last time, but now I can ask, what is the kernel? Well, that's the set of all functions in the domain. So remember, this is differentiable functions. Such that df by dx is equal to the zero function. Okay, now that's some set of functions. Anybody know what set that is? Anybody give me a short description of that set? It's a set of differentiable functions so that the derivative is just zero.
So like all constants?
It's all constants, exactly. It's a set of all functions f in f so that f is, f in D, I guess, differentiable functions. F is constant. Because if f prime is zero everywhere, then f has to be constant, right? That's the kernel. And that's a subspace. It's a legitimate subspace. By the way, can anybody tell me, okay, well, no, we'll get to that later. Okay, what about the range of T? Okay, so in this case, the range is actually something that's not so easy to describe. It's a set of all functions G in a set of all functions so that G is equal to the derivative of some function. So G is equal to f prime for some differentiable f in D. Now, there's not really a very concise way to write what that is. You could use the fundamental theorem of calculus, right? So if G equals f prime, then for which so if there is a G with this property, then how do I find f?
You could integrate.
You could integrate, yeah. So then this implies that f equals or f of x equals integral from 0 to x g of x dx, right? By the fundamental theorem of calculus. So I mean, this example, if is not that important, and if the calculus is confusing you, you can ignore it for now, because we won't really be looking at the range of such operators later in the course. But this. If you wanted to describe this more exactly, this would be a set of all functions such that G is an integral of some other function. So not every function has that property, right? For some differentiable D, for some differentiable F. Okay, so that's not. Okay, maybe that's not such a great description, but anyway, this is what the range is. So now, is this one-to-one?
No.
No, why not?
Because if you integrate, there's like a constant, so it's not just one solution.
Good answer. So no, because df by dx equals b, let's call it, has multiple solutions. Namely, the solutions would be whatever you get by integrating this plus a constant, right? So you would right. So right. So if you wanted to solve this, then you would integrate both sides. F is equal to integral b dx plus c. That's one way to see it. But within linear algebra, there's a sort of more immediate way to see it. It's one-to-one if the kernel is the trivial subspace, right? Here, what's the kernel? It's not trivial, right? It's a subspace of constant functions. No, because the kernel is not this. Okay. So these are really two interpretations of the same fact. Excuse me, why shouldn't the bracketed thing switch the G and X like it's in the box? Sorry. I'm a little confused by your question. I'm trying to solve the equation G equals F prime. I'm trying to find an X. And so I integrated both sides. I got F of X. Oh, I see. You're saying this X appears in too many places. Maybe that's what you're saying. Okay, good. Thank you. This would have to be a new different variable, right? Like let's say Y. Was that the issue?
I think they're asking because we said G is F prime, and then F is integral of G, but in the the curly brackets we're saying G is the integral of F instead of F prime.
Oh, sorry. Yeah. Okay, fine. Oh, you mean, oh, I see what you're saying. Right. Okay. Yeah. Thank you. Sorry, this is just a mistake. Okay, so I'm trying to solve the equation G equals F prime. So I'm asking what is the set of G, so the G equals F prime. In the box, I integrated both sides, and I got that there is a solution. Actually, there are many solutions. I guess there's a plus C here. Okay. Oh, I see what you're saying. So yeah, okay. In some sense, what I wrote in the curly brackets doesn't actually give you yeah, okay. It doesn't actually give you a nicer description of the range. We'll just leave the description of the range at this. Okay, sorry, that was just a mistake. It's the set of functions that are derivatives of differentiable functions. And I actually don't have a very nice description of what that set of functions is right now. It has something to do with which functions are integrable, but I don't want to get into that. Mm-hmm.
Oh, could you explain the relationship between 1 and 2 for like why it's not 1-to-1?
Yeah. So this comes down to this fact that here I said that kernel of T is empty if and only if Tx equals B has at most one solution for every B. Right. And so here what I'm saying is that T of X equals B has multiple solutions. Right. That's in terms of the transformation, that's what item 1 is saying. But then according to star, that's the same as the kernel not being empty. So these are the same thing by a star. Does that answer the question?
Yeah.
Yeah. Okay. So don't worry about this range thing actually, because I don't want to get into subtleties of calculus because I want to focus on the linear algebra. Maybe focus on this kernel example. That's simple enough. Let's look at another example. So this example is going to be a linear transformation going from the set of polynomials of degree at most 2 to the set of polynomials of degree at most 3. And it's going to be defined by T of any polynomial of degree at most 2 is going to be the polynomial you get by multiplying that by the variable T. And so when you do the multiplication, you get that it's this, right? And this is in P3. So now when you first see this, you might say, oh, it's multiplication, right? So maybe it's not linear. You're not supposed to multiply things. right? But I'm never multiplying two vectors in this, right? I'm multiplying the input vector, which is this degree 2 polynomial, by the variable t to get another vector. And this multiplication is linear. You can check that it satisfies linearity. So this is a linear transformation. And now let's ask, what is its kernel? So the kernel of this is the set of all polynomials in P2 such that t times that polynomial is equal to 0. Okay, so which polynomials have the property that when you multiply them by the variable t, you get 0?
No. If she didn't give you points for the one, she's fine.
Sorry?
Yeah.
Oh, could you maybe mute yourself if?
For the next one, why?
Yeah. So which polynomials have the property that that when you multiply them by t, you get 0? Only 0, right? Any non-zero polynomial multiplied by t, you're not going to get 0. So this is 0. So this is 1 to 1. And now what about the range of t? Well, that's the set of polynomials q of degree at most 3, so that q is equal to, this form, a naught t plus a1 t squared plus a2 t3 for some a naught, a1, a2 in R. And so is that everything?
It doesn't factor in constants.
Yeah, it doesn't include constants, right? You can never get a constant polynomial as an output of this linear transformation. So this is not equal to P3. So this thing is not onto. So that's 1 to 1 and onto. It's the same concept as before. Any questions about these examples?
Can you repeat how is not equal to P3 again?
Oh, so in particular, this set here, the polynomial, any constant polynomial is not in this set. Like let's say the polynomial 1. Right, so that's a polynomial that's in P3, but it's not in the range because, I mean, another way to think about the range is it's all polynomials whose constant term is 0. So okay, so actually, I mean, lots of polynomials, right? So the polynomial 1 plus t squared, this is in P3, but not in the range of t. Does that answer the question?
Yeah, thank you.
Okay, so that's 1 to 1 and onto. And now using these concepts, we will define what an invertible linear transformation is. So this is an important definition. If t is 1 to 1 and onto, so t is now going between could be between two different vector spaces. This is kind of the new twist, right? Before it was always going from Rn to Rn. Now it could go from some V to some W. 1 to 1 and onto, then T is called an isomorphism. And by the same reasoning as before, if it's 1 to 1 and onto, then the range is all of the codomain. So the range is, the range is everything here. And every b in the codomain gets hit exactly once, and so you can reverse these arrows. It's the same reasoning as before. It's actually not a new reasoning. So if you have x and it gets mapped to some t of x, then there is another linear transformation, t inverse, going from w to v. So if t is an isomorphism, there is there's only one. There's a unique linear transformation t inverse from w to v, such that it undoes the action of t. and vice versa. T of T inverse of y equals y for all y in W. So so this is called the inverse. Same as before, just in this new language. Now, we talked a lot about inverses before. You know, the midterm. We talked about inverses of matrices. We talked about inverses of linear transformations. And now I want to emphasize a very specific property of linear transformations, which we'll use later in the lecture when we talk about the correspondence principle. So the key property, or maybe before the key property, let me give you an example of a isomorphism. Let's consider the map going from P2 to R3. Okay, these are two different linear transformations, which takes T, so it takes a polynomial, and all it does is it just writes the coefficients in a vector. Right, so this input was in P2, and the output is in R3. That's a linear transformation. You can check. And you can check it's one-to-one and onto. I won't do it here. It's kind of easy. You just check that if T of a polynomial is 0, well, that means, that means all its coefficients are 0. So that means the polynomial is 0. So that means it's one-to-one. And if it's, and to see that it's onto, well, you can certainly get any vector in R3 just by plugging in those numbers as coefficients of a polynomial. So this is an isomorphism. And the point is that so the key property of isomorphism that I want to emphasize is that an isomorphism preserves all linear dependencies between V and W. So an isomorphism preserves all linear between, maybe between is the wrong word, or well, specifically I mean this. So if you have some linear dependence in V, then this is if and only if the same thing is true on the other side, but now with the images. Okay. So now, why is that? So this is, well, it's kind of well, the proof is actually, let me just show you the proof. How do you prove this direction? Anybody know? How do you, suppose I tell you the left-hand side is true and I tell you T is an isomorphism. How do you get the right-hand side?
You could take the transformation of both.
Yeah, just take T of both sides, right? But now suppose I give you the left-hand side. How do I get the right-hand side?
Would you apply the inverse? Because
Yeah,
you
you'd
know it's
apply
an
the
isomorphism.
inverse. Exactly. So that's where you use that it's an isomorphism. If it's not an isomorphism, you can go one way, but not the other way. But if it is an isomorphism, you can go both ways. And this is a very powerful thing. The word isomorphism is a Greek. It means same structure. And one way to think of isomorphism, which is actually fairly accurate, is it's almost like, for the purpose of linear algebra, the two vector spaces are the same. You're just renaming the vectors using T and T inverse. Everything that's true on one side is true on the other side, and vice versa. So we'll use this fact in many examples in the coming lecture, but Any questions about this, the idea of this? So you see why it's important to have the inverse, right? If you didn't have the inverse, you could only go in one direction.
If you didn't have the inverse, couldn't you say that, couldn't you take all the constants inside the transformation, like using properties of linearity, and then show that it would have to be 0? Like,
No, you would have to know it's 1-to-1, right?
oh, yeah, okay, yeah, sorry.
So okay, you're catching a very important and interesting point, which is, so invertible means 1-to-1 and onto, right?
Yeah,
So 1-to-1 means you can do the argument you just said, that if you have vectors on the left-hand side that can be represented this way, then you can go backwards. But if it wasn't onto, then you wouldn't, then you wouldn't be able to. So the point is, let me write it completely symmetrically. Suppose you have a linear dependence of some arbitrary vectors W here, right? If it wasn't onto, you wouldn't be able to go back. So you can do the same thing like this as well, right?
yeah. So it being onto allows us, and 1-to-1 allows us to go back and forth, right?
Exactly.
Okay.
So being 1-to-1 and onto allows us to always be able to go back and forth for any linear dependence, either in V or in W. You can go back and forth by applying T inverse and T. And that's
Okay,
why
thank
both
you.
1-to-1 and onto are important. It's a very good question. So maybe I'll just flatten this arrow since I've run out of space. Okay. Any other question about this?
Is this a unique property of like what we're looking at now, or was this also true with linear transformations described by matrices?
This was true before. We just weren't emphasizing it.
Okay.
So you can do the same thing with matrix inverses. And it was true before. But we're now going to use this in sort of a very interesting way to reduce linear algebra in V to linear algebra in Rn. So, okay, so this is an example of an isomorphism. And so what do I mean by this principle? For example, suppose I'm interested in some statement in the world of polynomials. So suppose I have this question: is this set of polynomials 1t or 1 1 minus 2t plus t squared, 1 plus 2t plus t squared? This is a subset of polynomials in P2. Is this linearly independent? Well, I mean, okay, so now we're in this unfamiliar setting, right? But so what do we do? Well, by what I wrote on the previous slide, because you have this isomorphism, you have that these things are linearly independent if and only if the transformations of these things are linearly independent. Are linearly independent. But now these things are happening in different vector spaces, right? This is linearly independent in R3. Right? So this is where I use the isomorphism. But now wait a minute. This is something I know how to solve, right? So let's just write down what these vectors are. This is the vector 1, 0, 0. This is the vector 1, minus 2, 1. This is the vector 1, 2, 1. These are linearly independent in R3. Do you know, you know how to solve that question, right? How do you solve that question?
Augmented matrix?
Yeah, you just do row reduction, right?
Reduction.
So you do row reduction and okay, I mean, Okay. Do we want to do the row reduction here? Okay, you do row reduction, and you indeed get a pivot in every column. And so the answer is yes in R3, right? But then all these things are if and only if, so the answer here has to be yes as well. This is the power of an isomorphism. If you have an isomorphism between your vector space and let's say Rn, you can turn questions in that vector space into questions about row reduction and the answer any question. Because in linear algebra, any statement we talk about is ultimately a statement about linear dependencies. So what we're going to do in the rest of the lecture is show how to do this always. How do you always find an isomorphism that allows you to do this? But any questions about this example? Okay. So to always be, so the question, the one motivating question for what I'm going to do is how can you always do this? And the answer is with a basis. Okay, so basis is again something you learned about before the midterm, but we're going to learn it again, but now in this slightly more abstract setting. So definition, a basis of a vector space V is a list B1 through Bn of vectors in V such that two things are true. The span of the vectors is equal to V, and they're linearly independent. Okay, so this is again saying that there are enough vectors to span the vector space, but they're not redundant. Okay, so for example, this is a basis of P2. Why? Well, the span of these vectors is clearly P2. Because you can, you can write any polynomial degree 2 as a linear combination of these. And why are these linearly independent? Well, if you have some linear combination of these things, it looks like this, right? C1 times 1 plus C2 times, or I guess I'm using A's here, so let's call it A's. A0 times 1 plus A1 times T plus A2 times T squared equals 0 as a polynomial. Well, that means all the coefficients are 0, right? So indeed, they're linearly independent. So this equals means as a polynomial, right? So if two polynomials are equal, their coefficients have to equal. So indeed, it's a basis. Here's another example, something we saw earlier in the lecture. Let's look at a kernel of this differentiation operator, right? It's a set of constant functions. Anybody know a basis for that subspace? So it's a set of constant functions. Can you write that as a span of some vector or vectors that are linearly independent?
Could it just be one?
Yeah, just one. It's a span of the one function. So this is one vector is always linearly independent if it's not 0. So this is a basis of one vector. Okay, now we talked about basis before. Previously, we just emphasized that given a basis is a way to describe a subspace, right? So by the way, that's still true because remember, a subspace is just a vector space, right? So this includes the previous definition. So remark, V can be a subspace.
I'm confused about the kernel being the span of 1.
Okay, so what's the span of 1? Well, the 1 is the one function, right? So 1 means the function that's 1 of x is equal to 1. That's what this function is. So span of 1 means all linear combinations of the vector 1. So it's all functions that are type C times 1, right? In the space of differentiable functions. But a function that's some constant times this is a constant function. Does that answer the question?
Can you repeat the last sentence?
Yeah, so the sort of new conceptual thing that's going on here is you're maybe not used to thinking of functions as being vectors, right? So this one here is the constant function, right? If I take this constant function and multiply it by c, then that function is just the function that's c for all x, right? Does that make sense?
Yes.
So but then what is the set of all such functions? Well, that's all the constant functions. And the kernel was the set of constant functions, right? It's a set of differentiable functions so that f is constant.
Oh, okay, that makes sense. Yeah.
Yep, great. Constant means f of x is equal to the same thing for every x. Okay, so now we're going to emphasize a different, feature of having a basis, which was, kind of suggesting itself earlier. You have a set of vectors that spans V. So remember, spanning is an existence property, right? So what does this mean? This means every B in V is a linear combination of the basis vectors, right? And now because they're linearly independent, suppose I can write B as a linear combination, B as a linear combination. Let's not call it B, actually, it's a little confusing. Let's call it X. Suppose I can write X as a linear combination of B1 through Bk. How many ways are there going to be of writing X as a linear combination of B1 through Bk? Someone said infinite, somebody said one. So those are quite different. So anybody want to offer an explanation? Well, let's do a little argument. Let's do a little thought experiment here, right? Suppose I could write X as a linear combination of this basis in two different ways, right? Or I guess I'm using n. Sorry, I used n everywhere. I was using k. Let's call it n. Okay, so suppose I write X as a linear combination in one way, and then I write it in a different way. Does something bother you about this? Can the vectors be linearly independent if you have two different linear combinations? Let's add a little more space here. Or maybe let's even move this. Might as well use these features of Zoom. What would you do if these vectors were an Rn? Maybe you're getting a little nervous because you're not an Rn anymore. What would you do to these vectors in order to... So I claim that this is not possible. Actually, the answer is there's only one solution. Now,
Well, since B1 and B2 and up till Bn are the basis, they have to be linearly independent. And this is not linearly independent. So
well, why
there
not,
can
right?
only...
So why does having two solutions violate linear independence?
Well, this is also an if and only if statement for for when x is equal to 0. So then I think you can show that if you have two solutions for when x is equal to 0, then it must be linearly dependent.
Correct. So concretely, what you would do is you would just rearrange this, right? You would get that C1 minus C1 prime times B1 all the way to Cn minus Cn prime times Bn. is equal to 0, right? That's what you get by rearranging that equation. But now, because it's linearly independent, that implies C equals C1 equals C1 prime, etc., up to Cn equals Cn prime. Rearranging is a very powerful thing. So this argument then implies that actually every x in V is a unique linear combination. Okay, so that's the power of linear independence. It gives you uniqueness. Spanning gives you existence. Linear independence gives you uniqueness. It works just as well in any vector space. We didn't actually use any property of Rn in this little rearranging argument, right? So that's what I want to emphasize now. So when you have a basis of V, every vector in the space can be written uniquely as a linear combination. Okay, so what's the consequence? Or maybe I'll just write this as an important fact, which follows from our discussion. Every vector in V can be written as a unique linear combination. X is equal to C1 okay. And now I'm going to introduce another important concept. The weights in this linear combination are called the coordinates of X. So coordinates of X relative to B. So it depends on the basis. So okay, I'm going to use script B to talk about this basis, right? So let script B be a basis of V. And then now these are just numbers, right? N numbers. So I can put them in a vector. The vector C1 through Cn in Rn is called the coordinate vector of X relative to B, denoted X square bracket superscript B, subscript B. Okay, so let's maybe look at some examples just to make sure we understand what coordinates are. Any questions about the statement before I do the examples?
Are these coordinates just like coordinates in an XY plane? Can we think about them like that?
Sort of. I will tell you in a moment how they're more general than XY plane coordinates, actually. But
Okay.
XY coordinates are a special case of this. Okay, so it seems some people are confused about this slide. So could somebody want to ask a question? In the chat, it looks like some people are confused. So please ask. It's great to be confused. There's no problem. Just, because probably if you're confused, many people are confused. So we should talk about it more.
Every X in V is a unique combination.
Excuse me, could you repeat that?
Yeah, I was just wondering if you could re-explain why every X in V is a unique linear combination.
Yeah. Okay. So that's because of this little argument here, right? So let me now actually write it out in a little more detail. So suppose some x can be written in two ways, right? Suppose there's a vector x, and you can write it as two different linear, or in two ways, right? We don't yet know that they're different or not. Suppose there are two ways of writing it. So C1b1 plus C2b2 all the way to Cnbn is one way. And then C1 prime b1, sorry, I shouldn't have underlined that C1, plus C2 prime b2, etc., all the way to Cn prime bn is another way. Now, by rearranging, right, that means C1 minus C1 prime times b1 plus all the way to Cn minus Cn prime bn, that's equal to 0. Is that step okay?
Yeah.
Okay. But now you get to use linear independence, right? So the whole point is that they're linearly independent. So if I have a linear combination of b1 through bn that's equal to 0, then all the coefficients have to be 0.
Oh, right. So then C1 must be equal to
Yeah.
C1 prime. So that means that X actually cannot be written in like two different ways.
Exactly. That's the proof of uniqueness. So this is sort of a, I mean, we proved this earlier using pivots, but now occasionally, I mean, now somehow, you know, in the sort of more abstract linear algebra, you can actually prove everything without pivots. So this is the proof without pivots. The proofs without pivots are usually actually shorter, but more abstract. So this is the proof of uniqueness. Does that answer the question?
Yeah, thank you.
Professor, could you explain the kernel of D of ds again?
Sure. So previously in the lecture, we defined this. So are you okay with the step where we said it's a set of constant functions? So that's a calculus fact.
Yes.
Okay. So then literally we're just asking, can you express that subspace? So the set of all constant functions on R, can you write it as a span of some one function? And what we're saying here is that you can. This one is kind of arbitrary. I could have chosen any non-zero constant function. And the point is if you take the function 1, so just equal to 1 everywhere. So, right, the graph of the function looks like, it just looks like this, right?
Yeah.
Then if you multiply it by c, then, you know, you can get any other constant, right? So you can multiply it by, I don't know, some c and get any other constant function, and you can get all of them. That's all we're saying here.
Oh, I see. Thank you.
Yep.
Professor, I have a question about the following slide.
Yep.
Could you explain what capital B is in this case?
So this is just an abstract definition. There's no capital B in this case. This is saying capital B is the basis. Oh, sorry. Capital B is the basis. It's a set. I mean, it's a list of vectors, which is a basis.
Okay, gotcha. Thanks.
Yeah. So I'll do some examples. I think many people are rightfully confused because I haven't done examples with this yet. So let me now do some examples. Okay. So what's an example of a coordinate vector and a basis and this unique linear combination? So one example is what we wrote already here, right? So this isomorphism that we produced here actually is of the type that we did earlier. So for example, I have the basis 1t t squared, basis of p2, and I have a vector. Let's say this vector, let's say, I don't know, t plus 5t squared. That's a vector in p2, right? Can somebody, now the coordinate vector of this is the vector whose entries are the coefficients in the linear combination when you express this as a sum of basis vectors, as a linear combination of basis vectors. So what would be those coefficients? Well, t plus 5t squared. Can somebody write that as a linear combination of these three basis vectors?
Zero times 1 plus 1 times t plus 5 times t squared.
Yeah. So then the coefficients in the linear combination are these numbers 1, 1, and 5. 0, 1, and 5. You got to be a little careful here because there are two kinds of ones, right? There's the one that's the polynomial, and then there's the one that's actually a coefficient. So that's C1, C2, and C3. So if those are the coordinates. And if you put them in a vector, you get the coordinate vector. So in this case, this is actually not a complicated concept. It's just a different way of writing what we've been doing earlier. You get 0, 1, 5. And this is a vector in R3. So that's an example of a coordinate vector. Now let me show you another example. So somebody asked this good question that is this like coordinates in coordinate geometry? And the answer is yes, that's a special case of this. So here's one example. Let's take the vector space to be just good old R2 and take the basis to be just a standard basis. So let's just call it B, E1 and E2. That's a familiar object from before the midterm. Okay. And now let's consider a particular vector. So what vector did I prepare? Let's consider the vector x equals 3, 4. Okay, so that's a vector in R2. Okay, and I can write this as a linear combination of E1 and E2. 4E2, not 3. So what would be the coordinate vector of this vector x? Anybody know?
Three, 4.
Yeah, 3, 4. So this is a sort of a dirty secret. We've actually been talking about coordinate vectors throughout the course so far. What we've been calling vectors were actually just coordinate vectors of vectors in R2 with respect to the standard basis. So there's a picture associated with this. The picture is there's a two-dimensional plane, and there are these two standard basis vectors, which are like the standard perpendicular axes that you see. They're supposed to be the same length. I guess I should draw them to be the same length. And then, you have this vector 3, 4, which I guess looks like, okay, it doesn't look like that. Maybe it looks like this or something. Okay, that doesn't look like 3, 4 either. Sorry. So okay, so it probably looks something like, it actually is probably kind of far out here. Maybe it's here or something. And what is this equation saying? Well, it's saying that to get to that vector, you need to walk 3 steps in this direction, and then you need to walk 4 steps in this direction. Okay, that's the geometric meaning of this fact that is kind of familiar. But now the point is I could have another basis for R2. So same vector space, and let's now have a different basis. So it's called B prime, and let those vectors be these vectors: 1, 1, 1 minus 2. So this is some kind of like an alien basis, or it's just some other basis. Okay, it's a legit basis. It's these vectors span R2 and they're linearly independent. You can check that with row reduction. Now again, you have the same vector x equals 3, 4 in R2. So what's the picture now? Sorry, maybe I'll draw it here. The picture is that you still have the same vector x, but now your basis vectors are something else. So one of them is the vector. Sorry, this picture isn't very good actually. Let me tilt this a little more. So now your basis vectors look a little different. One of them is the vector 1, 1. So let's call these vectors B1 and B2. So this is B1. And the other one is 1 minus 2, which is maybe looks like this. Okay. These are actually not perpendicular. Maybe I shouldn't. They're not supposed to look perpendicular. Okay. And now to write the coordinate vector of x with respect to this new basis, I need to find the linear combination, the unique linear combination that expresses x as a sum of these vectors, right? So now these vectors are some very specific vectors, right? 1, 1, and 1 minus 2. Does anybody know how to find such a linear combination?
Matrix, augmented matrix.
Yeah, augmented matrix. Just do row reduction, right? So okay, let's do a little row reduction here. You have some augmented matrix, so 1, 1, 1 minus 2, and you want to express 3, 4. I already did it at home. I don't want to do it again. And you do row reduction, and you get that C1 is equal to 10 over 3, and C2 is equal to minus 1 over 3. Okay. So what is this saying? Well, this is saying that there is an alternate way to describe what this point x is. You now walk 10 over 3 units in the B1 direction. And then you walk minus 1 over 3 units in the, I mean, this is supposed to look parallel. Sorry, that doesn't look very good. Let me, you know. And then you walk minus 1 over 3 units in the B2 direction. And the point is, these are two perfectly valid ways to describe that same point x. Okay, so these are different descriptions of the same vector. And people have different ways of thinking about this intuitively. So one is that the basis provides a reference frame. And every vector has a unique address with respect to the basis. So the coordinates are the unique address with respect to the basis. And I mean, it's kind of like how when you measure anything, you have to have some frame of reference, right? So we may use north, south, east, west, but in some other, I don't know, civilization, they may use some totally different coordinates, like this B1 and B2. And nonetheless, as long as they're linearly independent in span, I can give a unique address to every point. So you can think of this as, different languages for describing the same object. Or you can think, I mean, these are all just metaphors, but strictly speaking, it's just given a basis, there is a unique address for every vector in the vector space, and that is a coordinate vector. And that vector is a vector in Rn for some n. That's a fact that we're going to use. So basis is like a coordinate system, but it's more general, right? Like, for example, in the right-hand side, B1 and B2 are not perpendicular. It is like a coordinate. It is a coordinate system, but it's a sort of general coordinate system. So any questions about this? Okay.
What wait,
yes.
what is the coordinate vector of B prime equal to?
The coordinate vector of, so B prime is not a vector, right? So B prime is a basis.
Yeah, I mean, sorry, the coordinate vector of x with the basis b prime.
Oh, yeah. Sorry. So, yeah, I never wrote it down. It's equal to 10 over 3 and minus 1 over 3. Because these C1 and C2 were, I solved, I did row reduction, right? So I actually expressed it as a unique linear combination. Sorry, I forgot to write that. It's 10 over 3 and minus 1, 3. So that's very different from the coordinate vector with respect to B, right? But, it's actually a description of the same thing, just with respect to a different reference frame. Any other questions on this example? Okay. I want to do one more example of a basis. Let's now look at a subspace of some two vectors, 1, 0, 1, minus 2, 1, 0, subspace of R3. Okay, so I'm going to draw a cartoon of this. This looks like some kind of a plane through the origin, right? And inside this plane, there are some two vectors. I mean, that's not a very good picture. Let's call these vectors B1 and B2. These are linearly independent, and they span. So maybe I'll draw them in red. They span this plane. They span this two-dimensional plane. Okay. Now H is a vector space, right? So B1 and B2 are a basis. This is a basis. Let's call this thing B. This is a basis of H, right? This is like the concept we learned before the midterm. But actually the same reasoning applies here, because a subspace is also just a vector space, right, in its own right. So this is still true. So now suppose I have some vector in this set. So let's take a vector x, and let's take the vector, I don't know, minus 1, 1, 1, which is easily seen to be equal to just 1, 0, 1 plus minus 2, 1, 0. So it's equal to B1 plus B2, right? So x is some vector. In here, it probably looks like this. So right now I use 3 numbers to describe x, right? Because in R3, you need 3 coordinates to describe x. Can somebody tell me what the coordinate vector of x with respect to this basis is?
1, 1.
1, 1, exactly. So this is the other. So you can apply a basis to you can apply this reasoning to a vector in a subspace. And what it gets you is it gets you a more succinct representation of that vector with respect to a frame of reference of that subspace. Okay, so this is another, certainly in applications, if you do later on in whatever area you're studying, this is another reason bases are important. If you know a vector is in a subspace, you should need less information to tell me where it is, right? Because you already know it's in the subspace. And so in general, the number of entries of a coordinate vector of a vector in a subspace with respect to a basis of that subspace, that'll be equal to the dimension of that subspace, not the, whatever the whatever the ambient dimension is. So this is another example to keep in mind. You'll be doing more homework problems with this. I'm not emphasizing this at this point in the course, but as per the definition, everything works perfectly well inside a subspace, because after all, a subspace is also just a vector space. This is the beauty of going to more general vector spaces, that you can treat even subspaces are just vector spaces. Any questions about that?
Can you explain why basis is 1, 1?
Why? No. Why the coordinate vector is 1, 1?
Yeah.
Because I expressed x as a linear combination with coefficients 1 and 1 of the basis.
Oh, okay. Yeah, thank you.
Yep. So remember, this is B1 and this is B2, right? Yeah.
So B1 and B2 are the basis for this subspace, not for the R3, right?
Exactly. B is a basis of H.
Okay.
Yeah. Any other questions?
Can you explain again why it is simpler to find a point when you know that it's in a subspace?
Well, so simpler in the sense that to describe the point, just generally, I need 3 numbers, right?
Yeah.
But to describe it in the basis of a subspace, I only need 2 numbers.
Oh, okay.
So there's a form of, well, I don't want to say compression because I'm not losing anything, but it's a succinct representation. It's like saying, I mean, one way of thinking about it is, if I want to give you directions to my house, the directions are going to be simpler if, if I already know you're in Berkeley, than if you could be anywhere in the world, right? If I had to, you see what I'm saying?
Yeah.
Yeah.
Yeah, that makes sense.
It's like that. Yeah.
Thank you.
Okay, so that's what I want to say about a basis for now. We'll come back to it later. But now let me get to the punchline. Let me now show you how using this concept of a basis and the concept of an isomorphism, we can always do what we did in this example. We can always reduce questions in vector spaces V to questions in Rn. So this is something which I call the correspondence principle. It's just something I made up. I mean, the terminology, but. So correspondence principle is based on a very simple observation. So suppose V is a vector space, and you have a basis for V, B1 through Bn. Okay. So what have we achieved? So you have V here, and you have a basis, B1 through Bn. Oh, sorry, that's not the right notation. Well, I told you about this coordinate vector, right? But now I'm actually going to think of that as a linear transformation. Okay, so this is kind of a meta thing to do. This coordinate mapping itself is a linear transformation from V to Rn. Right, so it's a linear transformation because if I take 2 vectors and take their coordinate vector, that is the sum of the coordinate vectors. You can check that. So this is a linear transformation. Okay, so we're using linear algebra to reason about a concept in linear algebra, which is a kind of funny thing to do, but it actually makes sense. You can use a language to talk about itself or its own structure. So the coordinate, this is, I'm going to call this a coordinate mapping. This is a linear transformation. Any questions about why that's the case? Okay. And now the punchline is that it's an invertible linear transformation. So it's actually an isomorphism. So there's an inverse linear transformation, which I can just, which is kind of the obvious thing. So define this transformation PB going from Rn to V by PB of a coordinate vector equals just the linear combination with the basis. And so the point is that this is a isomorphism. Okay, so the key is that this, so x goes to its coordinate vector is an isomorphism. This is true for any vector space that has a finite basis. That's important. Not all of them do. But for any vector space that has a finite basis, the coordinate mapping is an isomorphism. Now, what's the point of that, right? Well, the point of that is that any statement that's true up here is going to be true down there by what we said earlier about isomorphisms, right? What was the key property of isomorphisms? It preserves all linear dependencies. So any linear dependence in V, so the key new ingredient is a basis, right? The correspondence principle is that if you have a linear dependence in V, then it corresponds to a linear dependence of the coordinate vectors in Rn. Okay, so this is how you turn any statement about linear algebra in an arbitrary vector space to a statement in Rn. The key new ingredient is a basis. Okay, somebody asked, why did I write this as PB? The book writes it that way, and I want to be consistent with the book. Okay, so really the relationship is that, sorry, I don't know what this is. The relationship is that PB inverse is the same as the coordinate mapping. Okay, I know PB, I'm just calling it that because the book calls it that. So the key thing is that this is an isomorphism. Once you have a basis, you get an isomorphism from that basis. And that isomorphism is the coordinate mapping. And that allows you to turn anything happening in V into something happening in Rn. And then you can easily solve it there using row reduction. Right? So for example, you know, so let me just write the principle. Every linear dependence in V is accurately reproduced in Rn via the coordinate mapping. And vice versa. So the vice versa is via the PB mapping. Okay, so really any finite dimensional vector space. So okay, so I should say, so a vector space with a finite basis is called finite dimensional. And what they're saying is that any finite dimensional vector space is isomorphic to Rn. That's a one-line summary. So the lecture is almost over, but what is this good for? Well, it's good for two things. So you can turn any linear algebra problem about vectors in Rn into a problem about vectors in V into one in Rn. And the second thing, which answers a question somebody asked earlier, so we had this whole stack of theorems in Rn, right? We had too many vectors. We had not enough vectors. We had Goldilocks. We had the redundancy theorem, et cetera, right? And now it would be kind of a drag if you had to prove all of those again, right? I mean, not a drag. It could be a fun exercise, but okay. There's a sort of very slick way to get all these theorems for free. What we're going to do in the next lecture is I'm just going to show you that because of the correspondence principle, you just get all of these for free via the coordinate mapping. Sorry, via the correspondence principle. So just because of this isomorphism, you get all of the theorems now hold in this new generality. And I mean, if you have to draw a cartoon, it's something like there's V, there's Rn, and you know, the thing that connects these two things is coordinate mapping and this PB, which you should think of as, you know, as some kind of a, you know, some kind of a bridge that connects these two worlds. Okay, that's not a very good picture, but and the thing you need is a basis. Basis is very important. So that's all I want to say today, and we'll do more next time. But that's it for the lecture, and please ask questions if you have them.
Can you go back to the previous slides?
Yeah.
What is the word before basis? Like a vector space with
Finite basis.
Okay.
So that just means it's not infinite.
Thank you.